damaged structures is the newly constructed Siargao Gymnasium that suffered a partial roof collapse. But note that the design wind speed is significantly higher than the typhoon wind speed. Thus, if designed according to NSCP, ideally it should have been able to withstand the strong typhoon winds. So this research aims to evaluate if inadequate design is a probable cause of the partial roof failure of the Siargao Gymnasium. Specifically, it aims to verify that the design criteria conform with applicable design codes and standards, to evaluate the wind load carrying capacity of the roof structure, and to identify the weakest roof component and its failure mode. Here's the flowchart of the methodology. I'll further discuss each step on the next slides. For the first objective, the design criteria were checked to determine inconsistencies with design codes at this stage of the design process. For the second objective, we go on to the member and connection design check. First, the following design loads were calculated. Then prior to structural modeling, the member specifications were verified using attic survey observations. Then, the roof was modeled in SAP 2000 and a linear static analysis was conducted to obtain the internal interaction forces for design check. Unfortunately, there were unclear details and conflicting measurements in the structural plans, so assumptions were made based on applicable design references as well as common design and construction practices. Then SAP 2000 steel design check feature was used to obtain the demand to capacity ratios of trusses. But for purlins and member connections, the capacities were manually calculated while the demand forces were obtained from the structural analysis. Finally, the roof components with DC ratios greater than 1 were considered as under-designed. Lastly, the under-designed roof components and their failure modes that agree with the observed roof failure were determined as a possible initiating point and failure mode. Now I'll be discussing the results. Since the structure was built in 2019, it is likely that NSCP 2015 is applicable. So this is the code used in the design review. Most of the criteria agree with NSCP 2015 except the wind speed and exposure category. Instead of 210 kph, they use 200 kph, which upon checking is prescribed by NSCP 2010, although they declared to have used NSCP 2015 in their design criteria. Also, they use exposure category B instead of C that should apply to open terrain with small scattered obstructions. Thus, I run the following cases to consider 200 kph based on NSCP 2010 and 310 kph based on NSCP 2015. Now here are the results of the SAP 2000 steel design check of trusses. For case 1, all members passed, which should be expected since the parameters declared in the design criteria were used. While for cases 2 and 3, there were failing truss members. The maximum DC ratios are 1.229 for case 2 and 3.18 for case 3 that imply the high deficiency in capacities compared to the required loads based on NSCP 2015. Moving on to purlins, the purlin section is under design for flexural failure in all 3 cases, with DC ratios greater than 2. So this can be attributed to the relatively high CNC wind loads applied on the roof overhang, but note that the section also failed under MWFRS wind loads. On the other hand, the capacity of the purlin connection is enough to resist the loads in all 3 cases. Now, as shown in the tables, the anchor rods in the roof-to-column connection were inadequately designed for tensile, pull-out, and concrete breakout failure modes. But among these failure modes, pull-out failure will cover. To summarize the design check results, for case 1 that is as designed, the purlins and the anchor rods were under-designed even under loads computed using the design criteria. Then for cases 2 and 3, the trusses, purlins, and roof-to-column connection were inadequate to resist the respective loads. But in all 3 cases, the roof-to-column connection will likely fail first by the pull-out of its anchor rods. Now relating the design check results with the observed roof failure, one of ASEC's observations from their survey were the pull-out anchor rods as shown in the left image. The image on the right shows one of the first events in the failure sequence observed from a video footage where the truss was detached from a column. These observations agree with the design check results that the anchor rods were under-designed for pull-out failure. In addition, the truss was first detached from column C6, and as shown, the corbel area of this column suffered concrete damages. Thus, the roof-to-column connection of this particular column is the critical component in the proof failure. Synthesizing the results, The design wind loads were inadequate due to inconsistencies in the design criteria with NSCP 2015, although this is not the primary reason why the roof components were under-designed, since the purlins and anchor rods failed even under the loads computed using the design criteria. So there can be errors in the modeling, the design load calculations, or the member and connection design calculations. Then among the roof components, the roof-to-column connection will likely fail first by the pullout of its anchor rods. And given the limited pullout capacity of hooked anchor rods, AISC recommends to not use this type for connections with high tensile forces such as that in the shear gauge-nation roof. In conclusion, inadequate design is a probable cause of the partial roof failure of the shear gauge-nation. For a more accurate design review, the assumed dimensions and specifications can be verified by on-site visual inspection. Then, for future research, it is recommended to analyze the roof model under the actual wind loads to further prove the failure hypothesis. In addition, other failure hypotheses can be investigated to narrow down to the primary cause of the roof failure. And here are my references. Thank you for listening.